Hello everyone. Today we are presenting our work on designing and fabrication of a passive morphing wing using shape memory alloy, specifically nitinol. This project explores how we can make aircraft wings adaptive, lightweight, and more energy efficient by replacing traditional mechanic actuation systems with smart materials. Aircraft wings today are rigid, but flight conditions are not. During takeoff, cruise, and landing, the aerodynamic requirements are completely different. Yet we use the same fixed geometry wing. This creates inefficiency, reduced lift optimization, increased drag, and energy loss. Birds don't fly this way, they continuously change their wing shape. So the question becomes, why can't engineered wings adapt like birds? This inefficiency has real consequences. UAVs and small aircrafts operate across varying speeds and altitudes. A fixed camber airfoil can be optimal only for one condition. The result: 10 to 20% higher energy consumption, reduced endurance, increased structural loads. We need something lighter, smarter, simpler. So our research question was, can a camber morphing wing using nitinol SMA improve lift to drag ratio by at least 10%? How much strain can SMA safely deliver? What camber variation produces measurable lift improvement? Can this be done with lower power consumption than servo systems? If we answer these, we unlock a lightweight alternative to mechanical morphing. Our solution replaces motors with shape memory alloy, specifically nitinol wire. Nitinol has a unique property: when heated it contracts, when cooled it returns to its original shape. No gears, no heavy actuators, just smart material. We designed a 50 cm span wing using a NACA 2412 airfoil. The structure consists of carbon fiber spar, lightweight ribs, flexible trailing edge, 0.3 mm nitinol wire embedded internally. The SMA is controlled using Arduino Nano, MOSFET, switching 2S LiPo battery. Testing included camber deflection measurement, lift comparison, power consumption analysis. This idea is not just speculative. NASA and DARPA have tested SMA-based morphing structure. Research literature reports 8 to 12% aerodynamic improvements using camber morphing. Nitinol provides up to 4% recoverable strain, which is sufficient for trailing edge actuation. Our contribution is building a scalable, lightweight, student-level prototype that validates this concept experimentally. This project is structured across 4 phases. Month 1, airfoil design and simulation. Month 2, wing fabrication and SMA integration. Month 3, control circuitry implementation. Month 4, experimental validation and data analysis. The success metrics and how we define success clearly is at least 10% of trailing edge should be deflected, minimum 10% lift improvement, controlled actuation cycles above 500 repetitions, and the efficiency metrics are that power consumption should be lower than servo-based systems, weight reduction compared to mechanical actuation. We measure, not assume. The impact goes beyond a prototype. Adaptive wings can improve UAV endurance, reduce aviation fuel consumption, enable smarter surveillance drones, serve as foundations for next-gen aerospace structures. We acknowledge that there are risks. The risks can be SMA overheating, controlled duty cycling, and temperature limits. Fatigue failure operate below 4% strain threshold. Slow response time optimize to or for slow response time, we optimize wire diameter and cooling exposure. Every technical risk has an engineering solution. For this project, we are seeking 50,000 rupees to fully execute this project. Funds will cover the SMA materials, structural fabrication, electronics, experimental testing. With this support, we will deliver a validated morphing wing with prototype within 4 months. Aviation is moving towards smart materials and adaptive systems. The timing is right, materials are available, the problem is real. We combine aerodynamics knowledge, fabrication, capability, and UAV experience to execute this successfully. With your support, we aim to build the next generation of adaptive wings, starting here. Thank you.